Right. Well, good afternoon, good evening, good morning, depending on what your time zone is, and welcome to the INCOSE, that's the International Council on Systems Engineering UK Rail Interest Group. Our chair, Matt Gibson, unfortunately can't make it. So as previous chair, it falls to me, Bruce Elliott, to welcome you and introduce things, just to get some practical things out of the way. As I think you've all heard, if you're online, we are recording this so that other people can benefit from it who couldn't actually participate either in person or on Zoom. Right. So it really is an enormous pleasure to introduce my boss, Clive Roberts, Professor Clive Roberts, who's built here a remarkable capability in the general sense of railway systems. Let's not get hung up about what's systems engineering and what's other things. So not just systems people, though there is a significant modeling capability, but systems-oriented aerodynamicists, systems-oriented mechanical engineers, systems-oriented economists. And on that latter point, it really is a sad situation. I have to tell you that Paul Plummer, trained economist, by the way, who was going to deliver this talk jointly with Clive, has got the flu, we think, and can't make it. So Clive's kindly agreed to cover his part of the talk as well. So we're here in the buildings of the UK Rail Research and Innovation Network, which is attached to the Birmingham Centre for Rail Research and Education. A centre that is very much concerned with making a positive difference via systems thinking and all sorts of other thinking. And that, I believe, Clive, is going to be at the heart of what you're going to talk about.
Indeed.
So, time for me to shut up and let you get on with it. I should say, if you're on Zoom, I'll be monitoring the Zoom chat. So if you've got any questions or need anything, let me know. Over to you, Clive.
Excellent. Thank you very, very much, Bruce. And to follow on from Bruce, good evening, good afternoon, good morning, depending on where you are in the world. I think there may be somebody from Singapore, so it's very, very good morning in Singapore currently. I'm Clive Roberts. As Bruce has said, I'm Professor of Railway Systems here at the University of Birmingham. I've been here 25 years working in railways. When I joined the group that I now lead, and there was about 12 of us in 1997. Nowadays, there's about 160, 170 of us working in railways here at Birmingham. My background's in electrical engineering, but very much over time, I've become a systems convert. I do lots of systems teaching, both in the railway area, but actually across our civil engineering, mechanical engineering, and electrical engineering degree programs here at Birmingham. So not just about railways, and I participate in the INCOSE activities when time allows. Right. So as Bruce has said, unfortunately, Paul can't be with us today. But I'm going to cover some of the material that Paul was going to speak to. And we're really going to focus on systems thinking and customer focus for railway projects. And that underlying all of that is how we use modelling, simulation, and visualization and analysis to help make system-wide decisions in railways. Conscious, there's quite a mixed audience. I know some of the people in the audience and various backgrounds. So my intention is to start off by saying just a little bit about the centre here and what we do, so you get the context of where I'm talking from and the kind of work we do here at the university. I'm then going to very quickly talk a bit about systems in railways, very generally, just so we're all on the same page. And then I'll actually get to the point of telling you about the sort of the research work we're doing in this space. So rather than bore you with lots of things about the centre, we have a rather snazzy video that's about 3 or 4 minutes long. So I thought I'd show you that first, and hopefully Those of you online should get the sound. I think I've set this up right. So let's see if we can run that.
We are BCRRE, 50 years young, and this is us. Here we have 3,000 square metres of working space, laboratories, crazy cool machinery, and these guys. This woman solves problems. That guy drives trains.
I do.
We teach you all about railway engineering. It can look like this, or something like this. You'll hear technical terms such as
ducks are yellow,
Fish plates, headway, the 4-foot.
we like a good challenge and thrive being first to all sorts of things. The first hydrogen train on the UK mainline tracks? That's us. The first to offer a level 7 degree apprenticeship in rail and rail systems engineering? Us again. Winning the Queen's Anniversary Prize for higher and further education? Done. The first railway focus group to work in all non-Arctic continents? Well, you get the idea. Oh wait, we're also first with accredited B-Eng and M-Eng rail engineering degrees. Okay, what else?
We do all kinds of research.
Oh yes, we research stuff. And by that, I mean tons of stuff. We issued our first ever paper way back in the 1970s. Now we issue circa 100 per year. Easy. We're the only Russell Group university with a further education college, and it focuses on rail. We've had 3 spin-out companies. We've collaborated with big influential companies and companies that aren't so big yet, which led us to win around 30 awards.
more like 40.
All right, 40 awards. Did we mention that we have a railway station on campus? Well, we're the only university across the whole UK to have one.
We're BCRE. We're 50 years young, and we're just getting started.
So hopefully that gives you an idea of what we do here. And those of you here in Birmingham will see that you're in one of the buildings that's shown on the beginning of that. So as I said, the group here is 50 years old. We have a large education part to what we do, and actually I can see some of our current students in the room. We have about 300 students currently studying with us. We also lead something called UCRIN, the UK Rail Research and Innovation Network, and I've got a couple of slides on that in a minute just to give you a context of that. We do lots of things internationally, and we're very, very embedded in terms of the work that we do with industry. So have large partnerships here in the UK, but internationally partnerships with Indian Railways, SMRT in Singapore, and RTA in Dubai, but undertake work in all sorts of different places. The areas where we really lead, I think globally, align in that sort of technical leadership and strategy development, and particularly this systems approach, systems thinking around railway problems, but around railway operations and control, around data integration and cybersecurity, around smart monitoring and autonomous systems, the decarbonisation of railways and the challenge that we have around that, and particularly also infrastructure adaptation, climate change effects, those sort of things. How we introduce innovation. So one of the things I've learned over my 25 years here is that just developing some clever technology, and I guess this is perhaps the thrust of this presentation, just developing some clever technology isn't enough. We need to think much more carefully from the early concepts of ideas of the people, the process, how this is going to contextually fit into the system. And we obviously deliver lots of railway education and skills, but we also think about future railway education and skills and what the future railway workforce needs to look like. And if you think of perhaps some of those things I'm talking about, decarbonisation, digitalisation, our workforce, our current workforce, and those who are coming into the sector over the next 10 years will need quite different skills to perhaps what we've been conventionally training people with. So we're really interested in that, and particularly as part of that, how we get a more diverse workforce into the sector as well. So that's what sort of gets us out of bed in the morning, if you like. And then I guess the thing that's perhaps a little bit different, or very much our focus in the centre here, in all the work we do, is doing the stuff that you'd expect a university to do, which is the fundamental write a paper type stuff. All of my colleagues here write lots of papers each year. Not very many of them, or not as many as we would like, end up at the other side of this story in terms of being able to release products, making the world a different place. And in the railway area, we're really, really making sure that we have that impact. So, you know, our typical journey is write some papers, and this is for the hydrogen train. We wrote the first papers back in about 2010, 2012 around fundamental concepts of hydrogen trains. That turned into, this isn't a photocopier, this is the students' version of a first hydrogen train. And that was made in sort of the early prototype. We then worked and convinced somebody that we could be allowed a real train to do that on a test site as a proof of concept. And there's us standing in front of the train at COP26, where it was launched as a solution. And the thing that we like doing here is being on that entire journey. But in doing that entire journey, you can't do it on your own. You need to do it with collaborators and people from various stakeholders. So we're getting much better at accelerating this process and making sure we partner with the right people and get the right skill sets involved to get through those stepping stones. I'd like to talk to you about Ukraine because that's important in the UK context for rail. So Ukraine was funded back in 2017, 2018. I lead Ukraine, and it's a collaboration of academia and industry partners with a view to doing exactly what I said, accelerating the work we do at universities in rail and getting it out there into the sector, making it have impact much more quickly. In 2018, we launched 3 centres of excellence, and those of you in Birmingham are sat in one of them, which is the largest of the 3, which is the Centre of Excellence in Railway Digital Systems. There's a Centre of Excellence in Infrastructure at Southampton University and a Centre of Excellence in Rolling Stock at Huddersfield University. The funding model for this is 1/3 from government and 2/3 from private industry. So our industry partners are really embedded in what we do. We are holding hands and doing this very much together. And the grouping that we have is very inclusive. So we have a number of partners that have joined us over the time. So we have these digital centres, as I've said, work on testing led by Network Rail, our infrastructure manager here in the UK, RSSB, which is the Railway Safety and Standards Board, help us coordinate, and Unipart, who are a supply chain company here, help companies get a route to market if they need it. So we have our founding universities, which are the ones in the red here on the screen. The ones not in the red boxes have joined since we formed in 2018. And similarly, we have a set of founding industrial partners. They're the ones in the first box, and a set of industrial partners that have joined us since 2018 to expand our network. And we've had huge impact, both in terms of producing outputs, but actually also influencing government policy and strategy in rail and in the broader industrial sector in the UK and overseas as it happens. We're just going through a process of expanding our network, and in a few weeks' time, I will hear whether we've been successful with the funding request for 2 more centres. A Centre of Excellence in Through Life Engineering, which will be located in Goole, the top picture, the proposed centre there, alongside Siemens' new factory, where they're making the new London Underground trains, amongst other things. And then a Centre of Excellence in Testing, Validation and Customer Experience, which will be located in South Wales, on the site of the new Global Centre for Railway Excellence test track, which is a almost 7-kilometre test ring that's being built in South Wales. Again, we're doing that collaboratively with other universities, and we have a set of industrial partners that have together pledged £60 million of private industrial support to make this happen. So we are growing, we're expanding, and we're very interested in this whole space. And I think this new centre in part in Wales, hopefully at the end of my talk today, you'll understand some of the things that we might be doing in that centre beyond sort of sticking sensors on things when they do testing, which is probably what you might be thinking that we're trying to do. So I want to start by thinking about the whole system for railways and what that means. I know some of the people in the room don't come from a railway background, so I really want to start with really articulating what are the challenges in railway projects. And this is by no means a comprehensive list, but it is a starter for 10 of some of the things we need to think about as we're developing projects, particularly for rail, but other large infrastructure systems. So in railways, there is a significant amount of complication, complexity, and emergent properties. By this, I mean there are things where it's just very difficult rules to follow. That's the complication bit. The complexity bit is where we don't really understand the interfaces, and there's some subjectivity in how we consider the system in that way. And the emergent properties is where we put two things together and we get a different behavior because we've got those two particular systems coming together. And in railways, there's loads of those. If you think about the wheel and the rail and the squeal that it produces, if you think about the electromagnetic effects, if you think about gauging impacts and how things might change over the life of a vehicle, all of that makes this very, very difficult. The other thing in this background is to remember that railways are closely coupled. And by closely coupled, I mean they're in contact with each other or different interfaces all the time. There's loads of interfaces. And if we start changing things on either side of that interface, it affects other bits of the railway. That becomes a real challenge. Railways are very safe. It's a very safe form of transportation, but there is a trade-off sometimes between safety and dependability. And by dependability, I mean here, we want systems that are reliable, available, and have that safety to them as well. So there is a risk, we have a challenge that we introduce products into market that actually begin to fail early in service. There's a whole set of reasons for that in terms of, again, that complexity, complication, emergent property issue, but also around the small numbers of railway vehicles we might produce, or the bespoke nature of some of the things we do. Projects are very multidisciplinary in nature, and it's impossible for one person to understand and be able to explain all of the things that are required when you have a very complex and complicated project. There's, the world changes during the length of a project and through the life cycle of an asset. So a railway to come to fruition may take a decade or two from the initial planning to somebody actually opening the railway. If I was to want to go and buy a train today, it would take me 3 or 4 years to build up the specification, procure it, and maybe for it to be delivered. And then I'd probably want to be running it for 40 or 50 years. So these timescales are very, very, very long, and that creates challenges for us as well. We need to think about the whole life cycle, the need to design, build, operate, and maintain the phases of the railway, and sometimes that's difficult for us. And therefore, as a result of all of these things, we often struggle to deliver projects on time, to budget, and actually also, which is probably more about the focus today, is actually address the original need that is why we started to do it in the first place. We have a tendency to sometimes forget that, or at least forget the root driver, the reason, the customer focus for why we did things in the first place. This is not unique to railways, but railways do have this in spades all over the place, and you only have to read some of the trade press, or actually just some of the normal press, to find out where sometimes we don't get it right. So systems engineering can help in this story. Systems engineering helps us, systems engineering, system thinking helps us cope with that complexity and all the things that are wrapped up in that. It helps us to produce more efficient, economic, and robust solutions, and I'm going to show you some of those things today. Help us to prove that we've built the right system and proving we are building it right. We'll unpack that a bit as we go through. Coping with managing real-world changing issues. There's only so far we can go with that, but we think there's some real point there. And consider the whole problem, the whole system, and the whole system life cycle from concept to disposal. We believe, and as Bruce said, there's some people here in the centre that are very, very much focused on systems engineering as the definitive subject, where there's many of us that have systems in our thinking in terms of our research, but we believe that most projects can shave 10 or 20% off of the project budget by the use of proper systems engineering, systems thinking, and there's literature from around the world, other universities and other activities that support that sort of assertion. So again, just to provide a little bit of background, I like this graph rather a lot, because I think it sums up and helps people think about why early in design life cycles you should get the decisions right. So one of the things we know is that we commit costs in large projects like is that we have this need to commit lots of decisions about what we're going to build and why we're going to build it. The system's rebooting itself for some reason, but anyway, it'll sort itself out. So if you think about something like HS2 with the high-speed railway here in the UK, what we know is that early on people made decisions about how fast it should go, where the route should be, all of these sorts of things, and all of those decisions that you make really define the cost that you've committed. Now, you haven't spent anything, but by defining what you're doing, you haven't got much wiggle room later on if you want to change it. You've set the milestone for the sort of cost area you're in. If you think about if you want to go and buy a family car, it's the same thing. If you say you want something that goes at 200 miles an hour, you're going to spend an awful lot more money than if you're going to buy a round town runaround. And so if we don't get that right, or if we overestimate or underestimate, that's going to come back and really bite us later on. So this yellow curve here tells us that we're committing very early on in that concept stage, we're committing to roughly how much it's going to cost us. And before we even start delivering stuff, we may only have 10 or 20% wiggle room on prices. Now, if you think about HS2 in the UK, this high-speed railway is roughly going to cost about £100 billion. I wouldn't mind 10 or 20% of that. It'd be very nice, but all the same, that's not very much cost change that you have. You're not going to be able to cut large amounts out of the budget because you've set that very much in stone early on. So there's this dotted line on this graph that shows the cost influence, which is the inverse of that, which basically says you don't have very much influence quite quickly. When you start, you have maybe a blank sheet of paper almost. But then the red line is actually the money going out your bank account, as you're paying for it. So it's very late in the day comparatively that you're actually spending the money, but you've already committed it, you're not going to be able to change it. So all of that argues that early in the life cycle, as early as possible in the life cycle, you need to have much more certainty about what you're doing, why you're doing it, and that commitment that you're making is the right commitment. So that underlines all of the thinking around the research that we're doing. It's worth noting that this diagram came from something called the McNulty report, which was written in 2011. So it says on the slide anyway, which was a Department for Transport in the UK report looking at how to reduce costs in railways. And some of these things were raised at the time. And I know there's people in the room that wrote some of this report. And some of these things are still problems that we have in the sector. But this sort of thinking underpins all that we are doing in this space and what I'm going to talk about today. And then I quite like this graph, although it's a bit UK-centric, but it just is quite a nice visualization as well. So in the UK railway, we have historically used something called GRIP, which is basically a process stage, a life cycle stage by which Network Rail undertake projects. And this graph basically says that we leave all the validation till the end. So we do loads of stuff, and we sort of reduce the uncertainty as risk as we go along. But fundamentally, and I'm being a bit crude about this, but fundamentally at the end we turn it on and hope it all works. What we want to be able to do is bring that risk much more further to the left, and that's very much again the theme of what I'm talking about today is two things. That in all, we need to make the right decisions. That's the previous graph, and commit in the right way. And we want to try and get this risk. I'm going to talk about progressive assurance in a minute, but we want to get this risk left shifted. So earlier in the timeline, as much as we possibly can. How do we do that? Well, I'll talk to you about modeling, simulation, visualization of the results, and then the analysis. So I like a good V diagram. So as most systems engineers do, probably too much I like a V diagram. It's worth knowing, I'm sure everyone knows what a V diagram is like, so we'll explain it through quickly. I am very well aware this is an idealized view of a project, but it really helps me articulate and think about the stages in a project and what we're doing at those stages. So I like to sort of punctuate some of these kinds of talks with a V diagram so you can sort of get the gist of what we're talking about. And it also shows a little bit of where the life cycle in railways lies and what happens. So the V diagram basically says early on the top left, you think about what you're trying to do. You then start to write some requirements, and the requirements are basically what you want the system to do. You then get into some kind of specification, which is what you the processing of those requirements into what you want, what you need. That goes into some kind of system design, and that's this system definition bit on the left. Now, in systems engineering, we talk about the left-hand side of the V a rather lot, and we are going to do that today. But I would argue, and I think I'm learning much more over recent years, that the right-hand side of the V is equally important, but we don't talk about it so much, and we perhaps don't have so many solutions, and generally it's the forgotten bit of this. But then how do we bring all of these different bits that we've put together, all the components, subsystems together? How do we integrate them? How do we validate them? How do we make sure they are good for deployment and use? And there is an argument to say if you do all this good analysis on the left, then the right looks after itself. But in reality, there's still some more to be done on the right. And I said I would talk about that centre of excellence in testing, validation, and customer experience. That's very much focused on how do we do this stuff better so we get much more certainty. The other centre that we're working on is that through life engineering, which is actually that bit at the top, which is about how do we upgrade, do these updates and upgrades in those assets. Remember I said that a train might last me 40 or 50 years. How do I better build it so that I can maintain it and I can upgrade it and change it? So all of those things are wrapped up in everything that we're trying to talk about. So if we roughly encapsulate those into three things, some kind of business case development, some kind of system specification, some kind of testing and validation, we can sort of roughly, when I talk about life cycles a bit later on, you'll roughly know where I am. And the other thing that I think is really interesting is where the commercial interfaces lie in this V diagram. So in a railway context, it may well be the government that decides what the high level mission is and perhaps the early stakeholder requirements. And that's one stakeholder group. That may then be handed over to a network rail or an HS2, an administration that is then required to sort of flesh that out a bit, probably employ some consultants to help build up the specification. That then goes into a procurement process and somebody actually bids and wins that. Then they're down here building this, and depending on the contractual arrangements, other people may be integrating or bringing that together. Those interfaces, those contractual interfaces, those interfaces between contracts also offer us huge challenges. And one of the things that we don't have, and I'm hoping, again, the things I'm going to talk about help to bridge this, we don't have, beyond the sort of written requirements or the written specification or what the contract says, ways of communicating with one another very well about actually the traceability. If you're the poor soul down the bottom here, building a train door, actually understanding how the influence of your train door design has on that overall mission and desire of the end user. What you have is what's written in the contract, which may not be the greatest thing in the world. So to give you an example of this, you may be a train manufacturer and you may have taken on a requirement because you want to win the train build to get people loaded on and off of your train within a particular time. In reality, that's a much bigger system issue than your train. It's about whether people are told to stand on the platform correctly. It's about whether they've got actually information when they get to the station. It's about all sorts of things that are outside of your area of influence. And one of the things that we really want to do in our work is show that much more clearly to people so that we end up with proper specifications and these sort of systems thinking in this space. Because then we'll get these better systems for our customers and end users at the end of the day. And all while we're doing all of that, we want to do this left shift. So we don't want to come, remember that grip diagram where we have all the risk at the end, and that's here. What we want to do is get all of those risks understood at this stage. So we want to do this in simulation early on and understand where the problems lie and put the effort in the right place. And actually equally, in many cases where the problems don't lie in the level that we thought they might do, and we can spend a bit less money and we don't have to worry about them quite so much. So we believe very, very strongly that by moving things left earlier in the timescale, by not waiting till you've got the physical system, but having a systems level simulation of things, we can help reduce cost. We can reduce that overrun time so we're not suddenly having a oh darn, what's happened moment over on the right. And we can optimize the system capability. And I think this is probably my last sort of warm-up slide. You'd hope so, we're nearly halfway through, to sort of explain some of the work that we're doing. So that's sort of the narrative, and it's a big narrative, but actually it's a narrative that the industry has, but perhaps nobody really owns in the sector in the UK. And I don't think there's anything particularly different about the UK. I go around the world, and most railway projects suffer from the kind of problems that I've talked about. And actually, I think most infrastructure projects and big projects in general suffer from this sort of thing. It's just that they're much more evident in railways because of quite a lot of that close coupling, complexity, complication, emergent properties. So let's talk about the kind of things that we're doing in this space. And there's a huge team here at Birmingham that are doing all sorts of stuff in this area. But Gemma is well worth pointing out, because most of the slides that I'm going to show you that have any actual doing on them, Gemma's done the doing. So it would be amiss not to mention the great work that Gemma is doing. So I've sort of trailed this a little bit. I want to talk a bit about modelling, simulation, visualisation and analysis. Show you some of the tools we have that do this, and we've developed here at the university, but show how in those life cycle stages we're using some of these ideas and the kind of questions we're answering. Now, I'm a bit better, Gemma still tells me off, but I'm a bit better at being precise about how I use these words nowadays, because they mean different things to us, and we want to be a bit clearer about what we say, and you'll see some of the definitions as we go through. So why do we need to do this? I've probably said all of this before. Well, fundamentally, maybe it's no good one stakeholder having some clever way of modelling it. We need to have something across the sector that we share and know and we all use. We have this idea of saving money, ensuring business requirements are focused on throughout the project. So that's that traceability bit. Avoid differences in understanding between different stakeholders, de-risk the introduction of innovation or just new ideas, provide support throughout the whole life of the project, and ultimately provide a much improved service to customers. I hope that I will convince you that there is a solution to this. There just needs to be a push forward in this direction from a number of stakeholders. I think we were able to demonstrate that this is a solvable problem. We just all need to group together to solve it. So in the kind of things that we're really interested in is answering these sort of what if questions. What happens when a new line joins an existing line? HS2 is running trains on its new dedicated high-speed line, and at Crewe, it's suddenly going to go onto the West Coast main line. Is that a problem? Do we really understand that? Under which circumstances are we going to really have to worry about that? And when are we not going to have to worry about that? Who knows? Well, perhaps I'll tell you a little bit in a minute. Will this new timetable perform well for passengers? Believe it or not, for those of you in the rail sector, we generally don't know when we introduce things like this. We've got a rough idea, but we don't have that certainty. We sort of try it and find out and alter it a bit. It's a bit evolutionary in its processing. How can we solve those sorts of questions? What is the impact of introducing new rolling stock on a line? There's many, I could tell you many stories about this going a bit wrong, but how can we think about that? Which dispatching, driving strategy, whatever controller strategy works best on a particular line in a particular location? We don't really know. So what we've been working on for many years, as I said, the group was 50 years old last year. And I think our earliest simulation and modelling work dates back to about 1978, which was early analysis of the power system on the Hong Kong Metro line, and then just a couple of years after that on the Singapore Metro line. So we've been doing this kind of work in this group, albeit originally we used to do it in Fortran. Nowadays we have model simulators that I'll show you, but we do this kind of thing. So in terms of modelling, we can do sort of component modelling for one end, or we can do the whole railway and anything in between. And in terms of the decision support and answers we can give something that's a sort of simulator as a black box. It produces the answer 42 and we happily believe it, all through to something that is much clearer to understand what it does. And we have a quite nice way of trying to show that. and our simulation tools here. So the kind of thing we did in the late 70s was around our single train simulator. We have an updated version of it, but fundamentally the physics in it is exactly the same as it was in 1978. And that is doing a small model of a train and how much energy it uses going from one location to the next. And it helps us understand the power requirements for one small component, albeit a train is quite a big component, but one component of the railway. And we can do that on its own. We then have developed, and I'll tell you a little bit more about this, a tool called Brave, the Birmingham Railway Virtual Environment. That's about 7 or 8 years old, and we literally sat down with a blank sheet of paper. I remember the meeting where we sat down and said, well, if we were to do this properly, how would we actually do it? And we sketched out the architecture. I'm always amazed how good a job we did, if I'm honest, because whatever we want to do with this tool, it seemed to be able to do it. But what this does is bespoke simulation at sort of railway line level. We've extended that to what we sort of now call Brave in the loop, which means that what we have is, so this is a full simulator. Fundamentally on the computer, there's something that does what the railway does. Brave in the loop is like hardware in the loop. So basically what we can do is we can connect Brave, we can have a piece of hardware, and all the things that the hardware doesn't do, we can wrap Brave around it, and therefore we can force Brave, the piece of hardware, to think it's connected to a real piece of railway. You'll see a bit of that later on. And then we can move that to the next level up, which is digital twin, where actually what we do is we collect all of the data, or much of the data, from the real railway line, and we then use Brave to be the repository for that data as well. And then the stuff that's sort of we're doing just bits of at the moment is what we're calling synthetic, well, what the industry is calling synthetic environment, which is this simulation with the whole virtual railway and the whole ecosystem. So putting everything together, and how can we do that? So the sort of end point of what I'm going to talk about is up in that space. So, those of you who are techie and understand those sorts of things, this is an architecture diagram for Brave. What we have here is the operation of the railway. So this is the microscopic laws of physics bit of the railway. And the important thing is that we have this modular architecture that we can put things in and out of, and we have this interface. And this interface allows us to interface in that hardware in the loop way by putting other real systems in at the top, or put optimization algorithms over the top, or put other simulators on, as you'll see as well. So to give you an idea of what this looks like, this is quite an early simulation, but this is the East Coast Main Line running at about 500 or 600 times real speed. Down here is King's Cross Station, so one of the north stations in London. Up the top is almost Doncaster, so about 250 kilometres, something like that, of railway. And what we're doing, this is the old signalling system, or the conventional signalling system on this site, with the track circuits and points, and you can see the route settings and signals on this particular tab. And you can see underneath this all of the digital signals that are happening in the railway we can simulate. We've done loads of work to make sure that we know it's right, and there's consistency. No model is 100% correct, but we know where it's not correct, and therefore we know what it's good to be used for and not used for. And across that modeling, simulation, visualization, analysis stage, we've done a large number of projects in this spectrum. Some from the kind of stuff we're doing on HS2, I'll show you some of that in a minute. I think I'm going to show you a little bit about India as well. We're doing a whole sets of different projects in different spaces to try and bring together all of these ideas and use these tools. So I mentioned digital twin. Digital twin is a very overused term in the world at the moment. But fundamentally, what we're using our digital twin approach for is to collect real world data from the real railway and try and use it to predict how the railway operation could be optimized in real time, so at any one time, and understand the performance of the railway against what it should be. So this is probably the least, so we have some different ways of talking about digital twin, which start with BIM, Building Information Management, so just this existence, this map, this 3D representation of the railway, up to the things that we're doing in terms of simulation and co-simulation hardware in the loop. So we're doing this across the West Midlands area. And this video is probably the least sexy of the videos I'm going to show you. But this is us capturing live data from the train movements from London to Crewe, so a significant part of the UK rail network, catching those train movements and storing them in a way that we can replay them in our simulation environment. So we record these, we accept these into a form that can be replayed in the simulation. And then once we've got them in this form, what we can do then is put them back into the simulation and run them through. So we can have the real world, that's outside the window, the simulation that's running about, or the collection of the data running in a simulator that's running about 10 seconds behind the real world. The simulator can then be looking for issues. If issues are found in the timetable, it can then go into simulation mode and look at all of the future outcomes that might be the right answer. So whether that's rerouting of trains, cancelling trains, reordering of trains, those sorts of things. So this is the state of the art of what we're able to do in real time in this space. So this is some data collected through that method on the cross-city line, which is the line just outside the university here. And this is actually then using that to look at historical data. So this is showing what the real time is and what trains look like. This is this visualization piece. What is the usual dispersion of delays across those networks collected from that real world simulation? In HS2, we're doing something different because HS2 doesn't exist. So what we're doing is doing this from the design, and we're answering some of those questions that I posed earlier. So can HS2 withstand a disruption? Can we understand how planned actions can be mitigated? What can happen? How we can improve performance under under disruptions? So we've got a full simulation of the HS2 phase 1 and 2A. I'll show you that in a minute. And the kind of things we're using, bearing in mind this railway doesn't exist yet, is we're answering questions here that are then feeding into the specification. So truly left shifting this thinking. We're not waiting for the railway to be built and then worrying about how we might solve these problems. We're solving them now. So thinking very much about the robustness of the resilience of the railway as it runs. So this is our simulation of HS2, running a timetable in 2032. These are all the trains going up and down. This is modelling the ETCS and the ATO, the whole system. You'll see this where it's got the black name. This is where it's going through a tunnel. When it's got when it's changing in a neutral section. So anyway, the whole model is there, and we can run this model in all sorts of loops to understand those kinds of graphs and produce those kinds of analysis and graphs I've just been showing you. So we can start to understand, well, what happens if a train is late coming south down the West Coast main line? Does it matter? Where in the timetable does it matter? Can we change the timetable so that it's more robust to that? The other really interesting area we've been looking at is the depot, which is just in Birmingham here at Washwood Heath, and the movements around the depot. And again, there's some real challenges there in terms of the potential for the depot movements to disrupt normal running service, particularly if there's a slight delay on the network. So all of this can be decided now in some really traceable, understandable way and feed into that specification and making sure we change that specification correctly. In India, we've been doing something similar, but this is for upgrading a railway. So this is around a level 2 ETCS, so a signalling system upgrade. So we've been looking at what was the best way of rolling out some new signalling. The Indian government have made a commitment to rolling out new signalling in many places across India, but that's incredibly expensive. So how do you do that trade-off between full fitment of all the railway with the new signalling system and some mix? And if the answer is some mix, because that's the only thing that can be afforded, is which mix is the right mix of fitted and unfitted trains? So again, we've been running simulations of the railway line. We are running in the simulation, some trains being fitted and others not, changing the design of the ETCS system in terms of spacing between releases, and looking at what performance we get out of that, and then being able to show very clearly what will give us what benefits and what the cost might be associated with that. So this, I won't go into the detail, but this shows us where on the railway line we should be able to use what kind of system. And we have some real absolute understanding. Think that grip diagram again and moving everything left. We know darn well that we'll get the right answer, and this is how things will perform in reality. So then just reminding you of this architecture, the other things that we can do is we can put into here the passenger movement. So that example I was saying about dwell times on stations, for example, we can actually model the railway and the passengers at the same time and model the passengers going on and off the train and really understanding that interface and what happens when there's flows in either direction. We can put the hardware in the loop, like I was talking about earlier. And this is the signalling system, the CBTC signalling system in Hefei Metro, thinking it's connected to a real railway, where in actual fact, it's connected to a simulator. And we can integrate other simulators. In this case, and this line's in Singapore, and we're interfacing a power supply simulator to look at particular power supply faults. And this was really interesting. We were able to do the work here in the UK overnight to be able to repair a railway or redesign the power system of the railway so it could be implemented over the next couple of days in Singapore. What's this one? So the synthetic environment piece then brings all of that together and helps us create an environment where we can use all of those kinds of simulations at the various stages, and we have that handover. So we're using early simulations at that business case stage at the top left. We're then using the same simulations and augmenting them further as we develop the system specification. We're handing that simulation from one stakeholder to the next across the contractual divide. That can be then used by the subsystem manufacturer down the bottom to test and verify and validate their components. That can then be used for integration, can be used for testing, and actually can be used throughout the entire life. So this idea of the synthetic environment piece is to bring all of that together in one unified approach so that we can use it from start to end of our 10-year project or whatever, so that we are developing that capability, that modeling, that virtual asset of the railway in order to be able to do all of this left shifting and all this testing during our work. So this is what we're trying to do. This has huge impact on the cost, reducing the risk, making sure that the railway that we deliver has delivers for the customers what we intended it to do and why it did, and making sure that it provides us some value for money. So hopefully, you've got an idea that this systems approach to modeling, simulation, visualization and analysis can really help us make sure that what we're delivering has a focus for customers. And we really understand that, and we don't have the problems where we're rolling out systems, but then finding that we have complexity and complication we didn't understand. In order to do this, in most of the problems I've been explaining, there are actually these whole system problems. They're not one, can't be solved in one silo. They're operations and signaling and rolling stock problems. They're problems about the speed of the track or various other aspects. And we need to think about this as a whole system. This should give us the benefit of a better end-to-end journey. This sort of systems-led modeling, simulation, visualization, analysis has a huge role to play going forward, I believe. We're not utilizing this stuff enough. There's some really good reasons. It's quite hard, but I think we've been able to show through the work we're doing here that the bones of this is all possible. We just need to push forward and decide that we're going to do it. And that progressive assurance, doing stuff early, improved testing and validation are really important to make sure that what we roll out is a dependable system. So hopefully you've got a slight flavour of some of the work we do. we've got a bit of time for questions now, I think, Bruce.
Yes, and thank you, Clive. Thank you for going at a pace. It was somewhat like an X-Wing fighter coming into its final bombing.
You wouldn't expect anything else.
We don't expect anything else. And thank you for leaving time for questions. We do have some on Zoom. So my suggestion is that I'll deal with those. That's okay. But my suggestion is I'll ask the questioners to ask their questions, I think, because it's
okay. Yeah.
But we alternate between the room and the virtual world.
Indeed.
Questions for Clive from the room? Does anyone like? You want the microphone?
They won't hear you online unless you use it, so Jenny.
Okay. You were talking about a synthetic environment. How do you go about actually modelling the environment that the railway is in? Weather events, for example.
Yeah, it's a good question. So, in terms of being able to model the range of things that might happen in a railway, and weather is one of them, but just changing the capabilities of a train over its life or whatever it may be is the same sort of thing. Well, we can do that in a couple of ways. One is some of those things are predetermined and we can sort of understand. We don't need to know the precise relationships, but we can get a good idea of what might happen. So, for example, delayed and dwell times at stations. We know the kind of distributions that are expected from that. But equally, from bigger major events, we can learn from past history and past data. So, there's a whole talk I could do on AI and machine learning and various other things that has its place in this. But to be honest, unless we get the fundamental understanding of the railway right, which is the kind of things we're doing here, there's no point layering all that stuff over the top. You need to use AI and machine learning for the kind of thing that you're raising, is where we have some unknown distributions and we can perhaps learn a little bit from previous events of what might happen.
All right, so we're going to try and bring people in from the Zoom world. They'll be seeing you through that little camera, Clive.
Yeah.
Michael Whitaker, would you like to unmute yourself and ask your question? It isn't working.
Oh, well, is there a question to read, Bruce?
Yes, I'll read it. I think is probably. Oh, I say that I've got to work out how on earth to do it. I've just lost.
Michael Whitaker looks like he's at Euston. Not today, because they've changed all the passenger.
Let's do another one.
Okay, right.
So, Sanjeev Pichala, would you like to ask your question? I remember Sanjeev's question.
Okay.
He was talking about he'd heard Mr. Wild admit to some omissions on the Crossrail project, and his question was, how is this research going to help with those? And I guess there's an implicit question: is this research going to help?
I'm not sure I know the precise detail you referred to, but in terms of once things are perhaps rolled out, there's some challenges. And you enter a different phase. So the first point is if you would have done some of this sort of simulation work early on, you may well not have the challenges that are now faced. The second point, though, is to be able to test solutions. So I roughly rushed through an example in Singapore, but there what had happened is that there was an upgrade of the signalling system, and then a realization that actually the power supply couldn't cope with the upgraded signalling system, and therefore there was an undervoltage on certain trains which were tripping out the power system. So the railway stopped every so often. And
just a minute.
Oh,
so sorry, Bruce. Hi, Clive.
Hi,
I had a question regarding the applicability where does the system engineer come in? Because at the start of the project for large projects like HS2, system engineering is not actually called upon. Politicians make the decision and the system engineer comes in the middle of the life cycle. And we have to cope with the whatever is left and choose the alternative which is available to us. Now, for example, on HS2, ETCS plus ATO, the specification has got a single point failure, but nobody is talking about it.
Yeah, so that's a really good exemplar of perhaps some of the things that we were talking about in terms of that committing to the cost and doing it very early on, where by making those decisions, you're committed to a cost and you're actually committed to a risk profile that you may or may not have wanted to commit to. Now, I would argue that, and people, including Bruce, have done work here where we know that a number of projects take a long time to either just always take those things all the way through to fruition at the end. But when they are changed, it can take years for them to be recognised in projects and then addressed. Now, I would suggest that there are a number of reasons for that. One is that lots of people say stuff, but people say all sorts of stuff. And if you're sat on the board and if you're sat in a chief engineer's role, it's really difficult to try and work out which of those things you're being told are fundamentally showstoppers and really big problems, and which are people just getting on their high horse about certain things. And I believe that the kind of simulation tools that we're talking about here can early on, before all of that costs committed and all of that is committed, start to unravel some of that. There's a really nice example actually from a project called AirTrack, which was for Heathrow Terminal 5, which I think ran for 7 or 8 years, but fundamentally had a problem with level crossings, and was shelved in the end. And everybody on the project knew that was the problem, but nobody really had the wherewithal to be able to say, this is really a problem, it's not going to work. And so I think all of this is in support of systems engineers and engineers in general who are trying to design things in because they understand or feel that they're needed, but actually they don't have the backing or the traceability of their decisions. It can be a lone voice. The stuff, I'm not going into the detail, but the stuff we're doing around the HS2 depot, the senior person we're talking to at HS2 said, yeah, I knew that was the case, but I can see it now. We can make this argument now. We can make the business case because we've got it. Otherwise, there's a risk that things would have moved forward without that design change. So this is all about supporting people in that case. Sometimes, unfortunately, as you're suggesting, Sanjeev, things get built in very early on. There's a problem that if they just stay there too long, you're not going to get rid of them. But hopefully, these sorts of tools help you understand the cost profile, help engineers, systems engineers explain the risk that you're carrying forward in the project or the cost you're carrying forward in the projects. These sort of arbitrary requirements that have entered into the project somehow, what they really, really mean. Because fundamentally, people don't understand this and how this might play out.
Yeah, thank you, Clive. Thanks for the information.
There's a comment here from Jag Singh, which is, I think, I'm not sure it requires a response, it's a comment. He writes, I think systems engineers getting involved in helping project managers write the contractual documentation in terms of what's needed technically by each party does help a lot. Something we tried to do in our last project, as the project managers don't always have the deeper technical understanding the engineers do. Indeed, and further than that, just having that traceability to something that is, a real good understanding between all stakeholders of why things are in specifications really helps as well. Okay, so any question from the room? Why don't you just ask and then Clive? I'll repeat it. God.
The need for progressive assurance very early on the left side of the recycling. So how do you see this affecting the current safety assurance processes, which heavily rely on making a safety case and the whole argument for why it was done when after
Yes, so and is those things are also yes. So the question is, how does the idea of the progressive assurance around all aspects, which is sort of space I'm talking about, impact assurance of safety requirements? And I think the two just reinforce one another and tie themselves together. This, for me, is all about providing more traceability, more understanding earlier in the project, whether that's for safety or whether it's business risk, basically. And we just don't do enough of all of that. And equally, in some cases, we're over-specifying things because we don't understand it either. So this enables us to test things and have much more certainty earlier on in the design. And again, without saying too much, but if you think of specifications that somebody might write for, let's say, a signalling system, and they're written by a team of systems engineers, consultants, stakeholders on the left-hand side of the V. If they're not tested through this kind of thing, there's a huge risk that, you know, the first time they are implemented is when they're in a contract and somebody's told exactly what to build. So the kind of things we're able to do is build those specifications in a simulation and really test whether they deliver what we expected them to deliver. And further than that, where the specification may be a bit weak, maybe a bit woolly about what's actually intended, and really highlight that actually if the specification was implemented in this way or is interpreted in this way, you get a different system, you get a different performance requirement. So I know a good example might be how ATO is implemented, automatic train operation is implemented. If you say, well, my train should have ATO, well, there's a load of different ways ATO could be implemented. If you implement it in one way, you might get much better recoverability on the railway. If you implement it in another way, it may be detrimental in certain instances. And I can think of some instances where that has been implemented in that way, and that is the case. But the specification wouldn't have been precise enough. And it's nobody. Well, asking yourself all those questions before you build the damn thing is got to be a good idea, and having some proof for it. Because there'll be people in the project team that know that some of the things aren't great, but it's very difficult to argue that without this sort of understanding.
Thank you, Clive. We are running over a little, but there are some good questions out there, and if people will forgive me, I'll take a couple more. Dale, let's try. Can you unmute yourself? And
yeah, can you hear me, Bruce?
Yeah, go ahead, please.
By the way, just so you know, your audio is faded out. I can barely hear you, Bruce. But yeah,
maybe because I haven't switched the microphone on.
I would explain it.
Is that better?
That might be a factor. Yeah. Yeah. Thanks. This Clive. This is a great presentation. Very, very good. Nice speed, as Bruce said too. I was just wondering. This is a bit coming in from the side here. But has there been any collaboration between your university or the entire collection of universities and some of the healthcare, study like teaching hospitals or universities involving airflow and air quality to bring people back into transit? So it's kind of a system of systems thing where we're looking at, modeling airflow maybe with fluid dynamics, both at a platform level and a passenger compartment level, that kind of thing.
Yes, it's funny you should mention this, but yes, actually, and for both COVID reasons and actually also for pollutants on, so pre-COVID, we've done work on looking at the passenger environment on trains, particularly on diesel trains, because really just to understand that better and what emissions may end up in the carriages, in the cars. But actually, as a COVID issue, similar things also have happened around airflow to reassure people. So we have expertise in that airflow and modelling. So within my group, I have people that do computational fluid dynamics of airflow in trains and around trains. We do lots of work on slip streams and ballast lift on high-speed trains, and I've got one guy in my group that's very interested in trains blowing over, which they do every now and again. But equally, that expertise can be put to the airflow through train carriages, and we have been doing that work, yes, for both those reasons.
Great, thank you.
Okay, So I did see John Elphick's hand raised at the back. With sincere apologies to those who've got unanswered questions, I propose to take just one more.
Okay, and I'm very happy to have the emails and talk afterwards. So yeah, that's fine.
You heard that, guys? Okay, John.
So, I was wondering, you mentioned right at the beginning about the new Euclid Centre in Wales.
Yep.
And you hinted that you might say a little bit about how about testing trains and putting instrumentation on trains and how that might link. I thought maybe you could just expand on if everything's going to be simulated, if everything's going to be digital, why do we need to test?
Exactly. It's a good question because I didn't say what I was going to say. So yes. So the question is, I spoke in the presentation about the new Centre of Excellence that we're hoping to get funded in testing and validation in South Wales, and one question, and it's a legitimate question, is why do you need a test track and a testing centre if you can do everything virtually? And the point is that what we want to be able to do is better testing, and we want to be able to have, again, a much better argument for why we're doing the testing that we are. And we want to get to a position that when we roll a train out, really at the moment in the sector, we're rolling trains out knowing they're safe. We're not really rolling them out knowing that they're dependable in the way that you would want to if you were, say, I don't know, Volvo rolling out new cars or something of that nature. And there's a number of reasons for that. One is because we only get a finite amount of time to do testing on a live real railway. And we don't, test track access is really quite difficult. So, and lots of, so I know from Singapore, so I'm a technical advisor to the board in Singapore Metro, and there's as they went to do their testing, I think something like a third of their testing on operational lines got cancelled because the driver didn't turn up or because something overran or various other things. So if you're trying to do testing, you don't ever get done the testing plan you want to do. The railway specifications in the UK and around the world say you must do some very, very specific physical testing. So you have to do those. And then you get a small opportunity to do some other testing. And there isn't a lot of science to some of the testing space. So what you get is all the things that went wrong on the last project sort of added onto the end of the test plan. What we want to be able to do is understand why we're doing that testing, being able to do some of that virtually and arguing that it's mathematically and realistically safer to do some of this virtually and taking one or two instances to reinforce the simulation rather than doing a load of stuff physically. But also, particularly as train contracts, so if I've mentioned that Siemens are building this factory to provide new London Underground trains. They've got a contract to deliver trains and then look after them for the next 30 years. It's in their interest that they're dependable trains, but actually the sector doesn't really have very much opportunity to think about some of this beyond just good design. So how do we embed all of that? So one point is the progressive early modelling assurance, getting rid of those risks. The second is then making sure that you understand exactly why you're doing the physical testing you are and how that traces and what it represents. You can do some really clever math stuff to prove that if you've got 1,000 tests and you've got a search space, that you've picked the optimal set of tests to do to give your representation. We're nowhere near that at the moment. And therefore we know and we can justify why we're doing the test and why they're important. And as I say, making sure that we're trying to move beyond just doing the safety test to get the thing signed off and into service and actually getting the dependability test done, which is a bit hit and miss at the moment.
So I think we are just a little over time. I would like to thank the people here and on Zoom for their attention and their questions. I'm sorry we couldn't get to them all. We will write to you for feedback. We, the RIG, are really keen to understand how to make these hybrid sessions work for everyone. So we'd be grateful for that. And one of the things we don't entirely know how to do with hybrid sessions is how to thank the speaker. But if, like me, you felt cheered up by that presentation because it shows the potential to make the world a better place, or if you liked it for some other reason, perhaps you might unmute yourself, even switch your camera on, and thank Clive for giving us this presentation. Thank you, Clive.
Thank you, everyone. Thank you very, very much.
Thanks, Clive.
Yeah, thank you, Clive.
I think we can close. That's it.
Thank you, Clive.
Thank you very much.
Thank you.
Excellent.
Thank you,
Thank you. I'll
Clive.
turn you off
Thank
on
you.
Zoom now. Thank you for joining.